Chalo bachcho, today we are going to learn Wheatstone Bridge from Unit 3, Current Electricity. I promise I will make this topic so simple for you that you will never forget it and you'll get full marks in your exam for sure. Okay, let's get started.
So let me start by asking you a question. We all know what resistance is, but think about it. How do you actually measure it with precision? Especially for, let's say, some tiny unknown wire. You can't just look at it and guess, right? There has to be a smarter way to do it. And the answer to that little puzzle is this very clever, very beautiful circuit that we're going to study today. It's called the Wheatstone Bridge. And it's an amazing tool for finding an unknown resistance with really, really high accuracy. So what is this Wheatstone Bridge, really? Well, the main idea behind it is actually very simple. You just have to think of it as a perfect balancing act. Now, this is the official circuit diagram you'll see in your textbook. And I know, at first, it might look a little complicated, but trust me, it's very simple. We have 4 resistors, R1, R2, R3, and R4, arranged like a diamond. Then there's a battery connected across 2 points, A and C. And the most important part is this thing in the middle connected between B and D. It's a galvanometer, and its only job is to check if any current is flowing through that middle path. But you know what? Forget the diagram for a second. To really understand this, I want you to picture something much, much simpler. Just think of a weighing balance. You know, a terazu, the kind you see at a vegetable shop. This is the secret to understanding the Wheatstone Bridge. On a terazu, what happens when the weight on the left side is exactly equal to the weight on the right side? The needle in the middle points straight to 0, right? We say it is balanced. The Wheatstone Bridge works on this exact same principle. So here's the main point, the most important idea of this whole topic. When the Wheatstone Bridge is balanced, just like our terazu, the galvanometer in the middle shows 0, a 0 reading. That means absolutely no current is flowing through that middle wire. We call this current IG, and in the balanced state, IG is 0. This special 0 current condition is everything. All right, now let's get into exam mode. To get full marks, we need to know the official rule and the formula for this balance condition. So pay close attention here, okay? In your exam, if you're asked what is the balance condition, this is the perfect answer. It is the condition for a balanced Wheatstone Bridge where the current flowing through the galvanometer is 0. That is, IG equals 0. Simple, direct, and full marks. And here is the magic formula, the key to everything. For a balanced bridge, the ratio of R2 by R1 is equal to the ratio of R4 by R3. Please, bachcho, I want you to memorize this formula exactly as it is. This is going to solve all your problems on this topic. So what does this formula really mean in simple words? It just means the ratio of the resistances in one pair of adjacent arms, that is, arms next to each other, is equal to the ratio in the other pair. The left side is balanced with the right side. See? Just like our terazu. Okay, we have the formula. But you know, in physics, we always have to ask how and why. And sometimes the exam will ask you to derive this condition. So let's quickly go through the proof. It's actually very easy and just uses Kirchhoff's rules, which we've already studied. Let's walk through this step by step. First, we start with our main assumption. The bridge is balanced. And what does that mean? It means the current in the galvanometer, IG, is 0. No current flows through the middle. Simple. Now for step 2, we apply Kirchhoff's junction rule at point B. If no current is going down through the galvanometer, then all the current I1 must continue and go through R3, right? So I1 equals I3. Similarly, at junction D, I2 must be equal to I4. Make sense? Okay, step 3. Let's apply Kirchhoff's loop rule to the top loop, ADBA. We get minus I1R1 plus I2R2 equals 0. Now for step 4, we do the same thing for the bottom loop, CBDC. We get minus I3R3 plus I4R4 equals 0. And finally, step 5 is just a little bit of algebra. From the first loop equation, we can write I1R1 equals I2R2. From the second, we get I3R3 equals I4R4. Now, if we just divide these two equations and remember that I1 equals I3 and I2 equals I4, we get our final condition. R2 over R1 equals R4 over R3. See, it's a very simple and logical proof. Okay, theory is good, but let's make it crystal clear with a tiny example. Let's say we have 3 known resistances. R1 is 2 ohms, R2 is 4 ohms, and R3 is 3 ohms. The question is, what values should R4 have to make this bridge balanced? Well, we just have to use our formula. R2 divided by R1 equals R4 divided by R3. So 4 divided by 2 equals R4 divided by 3. That means 2 equals R4 by 3. And simple math tells us that R4 must be 6 ohms. Easy, right? Now, for a very, very important section, I call these silent killers. These are the small, common mistakes that can make you lose marks in the exam even when you know the topic. So let's make sure we avoid them. So here's the first silent killer. A lot of students think the battery and the galvanometer have fixed positions, that you can't swap them. But that's not true. Because the circuit is symmetrical, you can actually interchange their positions. Put the battery where the galvanometer is and the galvanometer where the battery is. The bridge will still work and the balance condition formula remains exactly the same. So don't let a tricky diagram in the exam fool you.
Now, this one is the biggest and most common mistake, so please listen carefully. Students often write the formula as R1 over R2 equals R3 over R4. This is completely wrong, and you will get 0 marks. Please remember, the formula compares the ratio of adjacent arms. That means arms that are next to each other. So it's R2 over its neighbor R1 and R4 over its neighbor R3. The correct formula is R2 over R1 equals R4 over R3. Always remember this adjacent arms rule, and you'll be safe. Okay, great job. We have learned the concept, the formula, the proof, and the common mistakes. Now let's just zoom out a little and see the big picture. Why is this topic even important? So why does this matter so much? Because the Wheatstone Bridge isn't just a theory question. It is the fundamental principle behind the meter bridge. And the meter bridge is a practical instrument that you will definitely use in your physics lab to find unknown resistances. So if you understand this concept well, your practical exams are going to be a piece of cake. So let's quickly summarize. What are the key takeaways? First, a Wheatstone bridge is a circuit used to measure an unknown resistance. Second, it works on the principle of a balanced condition, where the current in the central galvanometer is 0. Third, the golden formula for this condition is R2 over R1 equals R4 over R3. And fourth, it's the core concept behind the meter bridge experiment. Just remember these 4 points. And I'll leave you with a final thought to ponder. We've seen how brilliant this bridge is at measuring resistance very precisely. But what if we could take other physical things, like temperature or pressure or strain on a metal, and cleverly convert them into a change in resistance? Could we then use this same powerful bridge to measure all those other things too? Think about it. The applications are actually endless.